Hello everyone, welcome to my channel. In this video, we discuss the concept of nodal analysis and few problems on the concept of nodal analysis. We have a procedure steps for nodal analysis. Before that, let us see the example of a node. Node is the common point where two or more elements are connected. At simple node, current division does not take place, whereas at principal node, current division takes place. Simple node is a node where only two elements are connected. Principal node is a node where two or more elements are connected. Procedure to be followed in nodal analysis are: identify the total number of nodes, assign the voltage at each node. One node is taken as reference node. Develop the KCL equation for each non-reference node. Solve the KCL equations to find the node voltages. Nodal analysis is applicable for planar and non-planar network. Number of equations required to solve an electrical network using nodal analysis is given by E equal to n minus 1, where n is the number of nodes. Using the procedure, we just try to solve few problems now. Let's see the first problem. Write the node voltage equations and determine the currents in each branch for the network. This is the network given to us. We have to write the node voltage equations and determine the currents in each and every branch. Let us apply nodal analysis concept here. Step 1. Step 1 is to identify total number of nodes. Node is the common point where two or more elements are connected. Let us identify the node points. This is one node point where three elements are connected. Let this node be A. And this is one more node point where three elements are connected. Let this be B. And I'll take this as one more node point. Let it be C, where two or more elements are connected. Number of nodes equal to 3. Step 2. Assign the voltage at each node, and one node is taken as reference node. I'll assign here as VA, this as VB, and this as VC. VA, VB, and VC. I would like to take VC as reference node. Reference node can be given voltage 0 volts. So it will act as like a ground point. VC is considered as a reference node, whereas A and B are considered as non-reference nodes. Next, step 3 is to develop KCL equations at each non-reference node. Let us start with A. Applying KCL at node A. Here current is entering, 5 amps is entering, and I am assuming that in these branches currents are leaving. I'll consider, let this be I1, I2, and I3. According to Kirchhoff's current law, sum of the currents entering at a node is equal to sum of currents leaving, or sum of the currents at a node point is equal to 0. Here, if you observe at node point A, I1 is entering and I2 and I3 are leaving. I can write here sum of currents entering equal to sum of currents leaving. From the figure, I1 is clearly 5 amperes. So I can write 5 equal to, and I2 equal to V divided by R, VA divided by R. As VC is equal to 0 volts, let it be a ground. So I2 can be written as VA divided by R. Resistor value is 10 ohms. Next, I3. I3 is given by VA minus VB divided by 3. Because current always flows from higher potential to lower potential. So VA is greater than VB. We can rewrite this equation as 1 by 10 plus 1 by 3 minus VB by 3 equal to 5. Let this be equation number 1. Next, we have one more non-reference node B. Applying KCL at node B. Here, let this be same I3, let it be entering, and I am assuming the other two are leaving, I4 and I5. According to KCL, sum of currents entering equal to sum of currents leaving. So I3 equal to I4 plus I5. I3 can be written as always current flows from higher potential to lower potential. So VA minus VB divided by 3. Whereas I4 can be written as VB divided by 5. And I5 can be written as VB minus 10 divided by 1. From the figure, we can write this as VA minus VB divided by 3. This as VB by 5. This as VB minus 10 divided by 1. Let me rewrite this equation. Minus VA by 3 equal to 10. Let this be equation number 2. Next step. Step 4. Solve the KCL equations to find node voltages. Solving equations 1 and 2 will get the value of node voltages. We get VA equal to 19.85 volts and VB equal to 10.8 volts. Right? Let us see the question. Write the node voltage equations. We are done with writing and determine the currents in each and every branch. We should find I1, I2, I3, I4 and I5. So I'll write here I1 equal to 5 amp from the figure and I2 equal to VA divided by 10. We got VA 19.85. 19.85 divided by 10, which is equal to 1.98 amperes. I3 equal to VA minus VB divided by 3, which is equal to, if you substitute the values of VA and VB, 19.85 minus 10.8 divided by 3, you'll get 3.01 amps. I4 equal to VB divided by 5, VB equal to 10.8 divided by 5 equal to 2.16 amp. I5 equal to VB minus 10 divided by 1, which equal to 10.8 minus 10 divided by 1, that equal to 0.8 amps. This is how, using nodal analysis, we can find node voltage equations and we can determine the currents in each and every branch. Let's solve the next problem. Determine the voltages at each node for the circuit shown. In nodal analysis, step 1 is to identify the number of nodes. Let's identify the node points. Node is the common point where two or more elements are connected. We just take this as node point where four elements are connected, and this as another node point, and this as another node point. In nodal analysis, always try to take principal node only where two or more elements are connected. Let this node be D. So total number of nodes equal to 4. Step 2. Assign voltage at each node. I'm assigning here this as V suffix A, this as VB, VC, VD. And we have to consider one node as reference node. And VD, I'll consider it as reference node, that is VD equal to 0 volts. Okay. Step 3. Develop KCL equation for each non-reference node. Applying KCL at node A. I just assume all currents are leaving this node. I1, I2, I3, I4. I'll write I1 plus I2 plus I3 plus I4 equal to 0. Sum of currents entering equal to sum of currents leaving, or sum of the currents at a junction point equal to 0. I1, I can write I1 as VA minus 10 divided by 10, and I2 can be written as current flowing across 5 ohm resistor, VA by 5, and I3 as current flowing across this 3 ohm resistor, VA minus VB divided by 3, plus I4 is same as I3. By rewriting this equation, I'll get 0.96 VA minus 0.66 VB equal to 1. Let this be equation number 1. Next, apply KCL at node B. Applying KCL at node B. You can see here, let it be same I4, let it be I3. Here current is entering, and I'm assuming here current is leaving. Let it be I5. I can write it as I3 plus I4 plus 5 equal to I5. Sum of currents entering equal to sum of currents leaving. I3, I4 and 5 amperes are entering into this node, and I5 is leaving. I can write I3 as VA minus VB divided by 3, and I4 as VA minus VB divided by 3 plus 5 equal to VB minus VC divided by 2. By rewriting this equation, I'll write 0.66 minus 0.66 VA plus 1.16 VB minus 0.5 VC equal to 5. Let this be equation number 2. Now I apply KCL at node C. This is I5, let this be I6, and let this be I7. Applying KCL at node C, I5 equal to I6 plus I7. I5 can be written as VB minus VC divided by 2. I6 can be written as VC by 1 plus VC by 6. This equation can be rewritten as minus 0.5 VB plus 1.66 VC equal to 0. Let this be equation number 3. Next, step 4. Solving all the KCL equations to find node voltages. Solving equations 1, 2 and 3. We obtain node voltages as VA 8.06 volts, VB 10.2 volts, VC 3.07 volts. That's all for this video. Thank you.